Hello, everybody. Let's get started with Unit 1, Part 3, where we're trying to understand the motions of the planets. Not only the motions of the planets as we observe them in the sky, but also the orbital motion of the planets around the sun. We are going to be addressing such fundamental questions of why do things orbit one another? What are the forces that are involved? What is this concept of gravity, or at least from a Newtonian sense? We don't really get into Einsteinian relativity here. It's a little bit beyond the scope of this course. But let's start by observing the planets in motion in the night sky. What we'll do is we'll take a look at a stellarium demonstration, and then we will sort of gather up what we observe the planets doing and realize that anything we observe the planets doing must be accounted for in the model of the solar system that we build. When we were first coming up with our ideas of what our solar system is like, we could only observe from our earthly vantage point, and therefore it was a little bit difficult. This is a tale that took thousands of years to figure out. So let me go ahead and bring up Stellarium. So you should be able to see Stellarium now. Let me go ahead and orient you to what I have going on. I just picked a time that would be advantageous to start at. So this is back in September of 2017. Don't worry about the time. I'm going to advance time by one sidereal day at a time. But notice that I have this red line on the sky and that the sun sits right on it. So this red line that's on the sky is the ecliptic, something that we talked about in Unit 1, Part 2. This is the path that the sun takes through the stars on the celestial sphere over the course of 1 year. So day after day after day after day after day, the sun moves along the ecliptic. Notice that all the planets that we can see, and right now we can see Jupiter and Saturn, they lie close to the ecliptic as well, and they're always going to lie close to the ecliptic. That's going to be one of our first observations. The moon sits near the ecliptic too. All right, so for this demonstration, it's best if I just pretend like we can see directly through the Earth. So one, I'm actually up in the daytime right now. That's why you can see the sun. But just so we can see what's going on with the stars all the time, I'm turning off the atmosphere and I'm turning off the ground. So we're not blocked by the horizon. Now we can just see the sun and the planets. So what I'm going to do is I'm going to advance time one sidereal day at a time. I'm going to go ahead and move this down here. So whenever I move time forward, it's one sidereal day at a time. This will move, and let me just go ahead and bump this forward. This is going to move forward by 23 hours and 56 minutes, one complete rotation. Why I'm going by one sidereal day, that'll keep the stars fixed in place. So the constellations will always be in the same place. I'm going to turn off the names of the constellations since they get in the way, but I'll keep up the lines. All right, so one sidereal day forward. Saw that the stars did not move, but the planets moved a little bit. So in a sidereal day, the stars remain fixed. Notice that the time is no longer 7 p.m. It's now changing by 23 hours and 56 minutes. It's 4 minutes shorter per day. Okay, so what I'm going to do next is I'm just going to hold down the advanced time by one sidereal day at a time so we can see the motion of the planets with respect to where the sun is and the ecliptic. Notice that right now we have Mercury, which is close to the sun, Jupiter, and Saturn. So let's observe what happens. All right, planets are all moving a little bit to the east. Venus and Mercury are sort of dancing around the sun, moving west and to the east, but Jupiter and Saturn, Mars are all moving to the east night after night. Oh wait, Jupiter, what are you doing? Why you stop, you slow down, you're moving backwards? You too, Saturn, why are you going backwards? What about Mars? Okay, nope, Mars reverse courses in the his course in the sky goes backwards. Oh, it's going normal now. Jupiter's moving back to the, wow, that's insane. That's a lot of planetary motions going on. Let me go ahead and back up to where we started. And let's take a look at that again. Let's see, we were in September. So we were right about here or so. Okay. So let's watch that again. And let's pay attention to Mars, particularly, while I'll explain what's going on. So as you see Mars, it's moving more to the east night after night. So south, southwest. Over here is west, over here is east. So it moves, planets night after night tend to move a little bit more eastward night after night with respect to the background stars, and always measuring with respect to the background stars. Mars is moving faster than the rest of them, other than Mercury and Venus, which are always close to the sun and moving the fastest. But you can almost picture the orbits they have around the sun as they move. All right, so notice that Mars and Saturn are still moving to the east. Jupiter is slowing down. Jupiter has kind of stopped, not moving more eastward or westward, but now it's going to start moving westward, or the opposite direction. Saturn's following suit in what we call retrograde motion. And now Jupiter is about to reverse course and start heading back in its normal direction, a little bit eastward night after night, what we call prograde motion. And now Saturn's doing the same. And as we progress time, moving forward, we lost sight of Mars, but that's okay. So, as we can see, planetary motion is a little bit wild and chaotic. The planets are not super well behaved in their motions in the sky. They're moving at different speeds from night to night. Sometimes they're moving prograde, more to the east with respect to the background stars night after night. Sometimes they're moving backwards like they are right now in what we call retrograde. And then we have Venus and Mercury, which are just dancing around the sun all willy-nilly, as if they're tethered to the sun. And there we have Mars. So let's go ahead and watch Mars and see what it's going to do. Moving prograde, always near the ecliptic. I'm not going to let Mars get away. I'm going to change my view. So we can watch Mars, still moving in a prograde fashion, not getting away. Just watching Mars. But now it's starting to slow down. Nope, it's still going. Now it's slowing down, stopping prograde, going into retrograde motion, still near the ecliptic. Retrograde for a little while, and then back to prograde again. A lot of things are going on with planetary motion. This is an incredibly hard thing to describe, and even harder thing to come up with a model that explains all of those observations. Let's see what we can do. And I want to go ahead and review what we just saw. So the motions of the planets with respect to the background stars is complicated. In fact, the word planet comes from the Greek word planetes, which means wanderer. So planets always appear close to the ecliptic. That's not so much wandering behavior, it's just restricted in where they can be. It tells us that our solar system is disc-shaped, it's flat, and all the planets orbit on the same orbital plane, or very close to the same orbital plane, the same plane that the Earth orbits the sun on. And planets can change their position relatively quickly. They are changing their position with respect to the background stars. They're wandering through the stars, and they're doing it so that they are actually changing their speed from night to night to night. They're not always moving at the same rate through the background stars. This also means that the planets don't have fixed equatorial coordinates. We can't say that Jupiter has this right ascension and declination. They're always zinging around the celestial sphere, always changing their right ascension and declination coordinates. Mercury and Venus always appeared close to the sun, and they had the fastest motion. This is going to be the evidence that Copernicus is going to use to make sure that they are closer to the sun than the Earth is. Their orbits are interior to Earth's orbit. Most of the time, the planets seem to move a little bit more east night after night with respect to the background stars, a so-called prograde motion. But occasionally and periodically, so they'll do it over and over and over at the same intervals, they'll stop their prograde motion, reverse course, and move toward the west with respect to the background stars, night after night, in what we call retrograde motion. And you couldn't really see it with the Stellarium simulation I was running, but if we were to observe the brightness of the planets during retrograde, we would notice that the planets are brighter during retrograde motion. This is the evidence that we need and have to build a model of the solar system. And we now are standing on the shoulders of giants who have worked on this question for thousands of years. But originally, the model of the solar system, the simplest one and the one that feels right because we don't feel the Earth rotating or orbiting the sun. It really does feel like we're at the center and everything's going around us as we observe things day in and night, for every day and every night. So it's sort of natural that people would come up with what's called a geocentric model first. Geocentric means geocentered, Earth-centered. So we plop the Earth right at the center. And then we're going to make everything move around the Earth. The Earth sits completely still at the center. And then the sun will have its own orbit around the sun, or orbit around the Earth, and so will the planets. Although Ptolemy, a Greek philosopher, reasoned out that to explain retrograde motion, if you just have orbits, so the planets just moved around in these perfect circles around the Earth, you would never observe retrograde motion. So he comes up with a solution to explain retrograde motion of, oh, instead of orbits, they called these deferents. So let's go to the Mars deferent, this big perfect circle. So Ptolemy was a prescriber to Aristotelian thought, which dictated that we could understand everything about the universe through logic alone, and that there had to be a perfect harmony, a perfection to the heavens, and perfect things, everything in the heavenly realm, everything outside of the earthly realm is in the heavenly realm. Everything in the heavenly realm must be perfect, which means orbits need to be perfect circles. Everything that is spherical needs to be perfectly spherical. Everything that is circular needs to be perfectly circular. Everything is perfect, no flaws. Flaws are only allowed in the earthly realm. So we have a perfectly circular deferent for Mars, but Mars does not travel on the deferent. Mars's epicycle, an orbit on an orbit, travels on Mars's deferent. So, and this epicycle is also perfectly circular. So here we put Mars, which would move at a constant speed around its epicycle, and Mars's epicycle would move at a constant speed around its deferent. So you can see as Mars would swing around this point on its epicycle, for looking from Earth, it would appear Mars would be moving backwards to how it normally looks. It would be moving retrograde. So that's how the most celebrated geocentric model, the Ptolemaic model, explained retrograde motion. And I do expect that you've probably reviewed these slides already. I am not doing a full treatment of the geocentric and Ptolemaic model here. Please go see the lecture notes for that. Notice that as Earth is just sitting still here, it doesn't have an orbit. That idea of using parallax to measure the change in position of the stars, the apparent shift the position of the stars as Earth moves around its orbit, that wouldn't happen. So this predicts no parallax. Another way we could build the solar system, and this is Copernicus's idea, or really Copernicus popularized a very old Greek idea and realized that this one is the more correct, the more in line with reality model. A sun-centered model, so a helio. So the Greek god for the sun was Helios. So heliocentric means sun-centered model, a heliocentric model. Here we plop the sun right at the center, and then we make the planets go around the sun on orbits now. So we got rid of deferents in their epicycles, which was horribly complicated, and we went with just orbits. So the most basic heliocentric model is the Copernican model. We'll talk about that in the next video. But we have updated the Copernican model quite a bit. It's a more complicated and better heliocentric model. First updated from the Copernican model to a Keplerian model, Johannes Kepler's view of the solar system. And now we're now at our current model of the solar system, which is governed by physics. So we have the sun at the center, and the planets move on orbits around the sun. And the further the planets are from the sun, the slower they orbit. You might be thinking, well, how does this explain retrograde motion, which is how I'm going to finish this video, and I'll show you retrograde motion in both the models with a simulation. But this one is going to naturally explain retrograde motion as an observational effect that happens whenever the sun, the earth, and a planet will all line up in a straight line. So if Mars is right here, it would be at what we call opposition. So as a planet approaches opposition and passes opposition, then it'll naturally give us a observable retrograde motion. And now Earth has an orbit, so this predicts parallax. All right, so understanding retrograde motion. I'm going to come back to these slides. I want to show you the two simulations of those models. So let's go with a geocentric model and see how it explains retrograde motion. All right, so right here we have the Ptolemaic model, and we're going to simulate. It's a Ptolemaic model simulator. It's not showing all the epicycles and deferents. It's only showing one deferent and one epicycle at a time. And right now I have this set to Mars. So here's the Mars deferent, here's the Mars epicycle, here's the Earth, slightly off in what's called a quant, but that's details beyond the scope of this course. We're not studying the Ptolemaic model in depth. So let's start the animation. So you can see the path that it takes overall in the red line. You can see right here the sun as it's moving around. So it's passing through the signs of the zodiac. And what I'm going to do is I'm going to turn on. So this is where the planet would appear to be amongst the background stars, which you can see down here as well. So prograde motion and then retrograde motion, prograde motion. Then retrograde motion, and it goes over and over and over and over and over again. Just to show you how this is kind of complicated, let's now do the sun line. We have that line. So you can see everything moving all at once. As you can see, this is a complicated model, a very, very complicated model. There's so many different moving parts. Every planet has its own deferent and every planet has its own epicycle, and it moves on the epicycle. And the speed it moves on the epicycle, while constant, is set for that planet's epicycle, and it can be a different speed for a different planet's epicycle. And each planet's epicycle moves on its own deferent, and the speed that it can move on a deferent is different for each planet and its deferent. Complicated, and how fast those motions are relative to the sun, all of that has to be accounted for. It is horribly complicated because it has so many different knobs you can twist, but because it has so many different knobs that you can twist, epicycle speed, epicycle size, deferent speed, deferent size, so it has so many different knobs, it was actually remarkably accurate at predicting the positions of the planets, much more than the original Copernican model. Let's take a look at a Copernican model. All right, so here we have a Copernican model. Here, I'm going to go ahead and change. Let's look at Mars again. So here would be Earth's orbit. Here would be Mars's orbit. And I'm just going to go ahead and start the animation. Here you can see where the planet would be amongst the background stars. Notice that as the Earth is going to catch up to Mars, it's going to start going into retrograde. At opposition, it's in retrograde, and then as it moves past opposition, it stops retrograde. Just a natural consequence of the setup of a sun-centered model. So going into retrograde, ending retrograde. Very simple, right? Few moving parts. Natural, easy explanation. We like such things, and this is why the Copernican model was so popular for so many. And I just want to go ahead and, since they are in the slides, I want to go ahead and orient you to how that retrograde motion works. So this is my own work. of trying to explain retrograde motion, or really the retrograde motion of Mars, with a Copernican model, which is going to have perfectly circular orbits, but Mars is farther away, so it'll orbit slower. And what we're going to do is so we have the orbital period of Earth. It'll go around the sun in 365.25 days. Orbital period of Mars is 684.5 days, so it's moving slower. And what I'm trying to do is explain the prograde, the eastward motion with respect to the background stars. It's happening most of the time. And then the westward retrograde motion happens near opposition, a natural consequence of a heliocentric model. I'm going to start with the Earth right here, and I'll put Mars just in its orbit right here. And I'm going to run out time for half a year. So Earth will complete half an orbit. In the same amount of time, Mars, moving slower, will complete less than half an orbit. This blue line is what we call a line of sight. Excuse me. This blue line is what we call a line of sight. And it is, if we are standing on Earth, looking at Mars, where would it appear amongst the background stars? So revolving counterclockwise, Earth would be rotating counterclockwise. So if I'm thinking about right here, rotating this way, so east is this way, west is that way. All right, so let's go ahead and watch. We're moving time forward 1 month at a time. So getting closer to opposition. And up here, you can see what it would look like in the sky from 1 to 2. So now we follow our line of sight, and it looks like Mars is now hanging out amongst these stars instead of these stars. It has moved in a prograde fashion more eastward. The length of the arrow, since every time step is 1 month, gives you an idea of how fast it's moving. The bigger the arrow, the faster it's moving through the stars. The smaller the arrow, the slower. Now at 3 months, and you can see the simulated view up there, it's getting close to opposition where the sun, the Earth, and Mars would all be in a straight line. Follow the line of sight. Mars is now hanging out over here amongst the stars. It looks like it's slowed down. It's prograde motion, but it's still prograde. So after a time of 3 months here at point 4, we are at opposition. So Mars is on the opposite side of the Earth that the sun is, and they're all in a straight line, a nice syzygy. But if we draw our line of sight from Earth, then it would look like Mars is now here amongst the stars. It has stopped its prograde eastward motion and turned around and moved westward. It's starting to do a loop in the sky. Then 1 month later, Earth would be right here. Draw our line of sight. It's still moving retrograde, but it's slowed down its retrograde, and it's hanging out here amongst the stars. So it's still drawing its loop-to-loop through the sky. There's our ecliptic. At point 6, it's starting to pull away in its smaller orbit, and it's going to start swinging around. And we draw our line of sight. We see that it's returned to prograde motion. And then after 6 months, we can see that it's sped back up and is now in its normal regular prograde motion. And we'll have to wait for everything to swing back around for the next opposition for Mars to go in retrograde again. So a nice, simple, natural explanation. All right, quick review of this. The planets make strange motions in the sky. They seem to wander through the stars, but there is a rhyme and reason to it. You can do observations of them, mark their positions in the sky, and actually catalog how they're moving. They're always near the ecliptic. They change their speeds. They have normal motion, which we call prograde motion. So most of the time they're moving more eastward with respect to the background stars night after night. They move eastward through the constellations. Sometimes they slow down and reverse their direction and move westward through the constellations, so-called retrograde motion. And that happens when the planets are at opposition, and that means that they're physically closer to the Earth is physically closer to the planet, so they're going to appear brighter if we adopt a Copernican model, or a heliocentric model with the sun at the center. And note that knowing the planetary position amongst the stars here is absolutely critical. It's those types of observations, very careful observations of the planet's positions amongst the stars and how they're changing, which is going to be the key observations that allow us to finally unlock and adopt a heliocentric model. So the rise of the heliocentric model is the next topic in the next video. Thank you for tuning in. And I will see you when we talk about the rise of heliocentrism.